Hey there. So, today we're going to get into talking about electrical circuits, just introduction to them, some of the basic components of an electrical circuit, the different values that you find in an electrical circuit, what actually constitutes an electrical circuit, how to how some of those different values are represented, and we're actually also going to be getting into the actual structure of, the atomic structure of electricity and kind of the building blocks of all this, and go from there. So, starting off talking about an electrical circuit, anytime you have uh, an electrical circuit, there's three basic components that you need to have. You need to have a voltage source, you need to have a conductor, and you need to have a load, something that's going to use the electricity. Could be a light bulb, could be a motor, could be anything. So the voltage source, this right here is I've got it drawn just as a battery. All right, so this provides a difference of potential to the circuit. All right, and then you actually have the conductors that carries the current through the circuit to the load and then back to the battery. And then the load itself is actually going to use electricity to, let's say, if it's a light bulb, it'll use electricity to provide light. Or if it's a motor, it'll use electricity to spin. And I've also got a switch drawn in here also, because that's how you would control, a motor or a light bulb, is with a switch. Turn it on and off. And what that does is that interrupts the flow of current through the circuit. So, talking about some of these terms I just use: voltage, current, and resistance. These are the basic fundamental values of an electrical circuit. This is how everything works, right? So you have voltage, which can be thought of as the electrical pressure through a circuit. That's going to actually push the current through a resistance to make work happen. Okay, so current is the flow of current is what actually does work, whether it's burning a light bulb or turning a motor. It's the flow of current that actually allows that to happen. Okay, and then resistance it can be thought of is the opposition to current flow. All right, so resistance, there's resistance in everything, even in conductors. There's a little bit of resistance, and if you have a load like, say, a light bulb, basically a light bulb is just a resistive element. So resistance opposes the flow of current through the circuit. So you need to have enough voltage or difference in potential to push that current through that resistance. All right. So that's, once again, this is just basic stuff, and we're going to be building on from here. Okay. So when we get down into the atomic level of electricity, you have different particles or different atoms. All right, atoms, if you remember from high school science class, they're the smallest part of an element. All right, and they can be charged either positive or negatively. All right, and when you have a charged particle or a negative particle, it's called an ion. Right, and then most people probably have heard opposites attract, like opposite charges attract, and then oppose opposites attract, and then like charges oppose each other. So that's what I've got drawn here. So these two, this is a positive and this is a negative. They're oppositely charged, so they're going to try to attract each other. They're going to go towards each other. Whereas these two are positive. They're like charges, so they're going to oppose each other. Just the same as if you have a magnet and you try to, if you try to push two positive ends of two magnets together, they oppose each other. You can feel that, right? So, and so you got these charges right here. You got positive and negative that attract, and then the like charges that oppose each other. All right. So, and when I say charge, it can be thought of as just a quantity of electricity that's either positive or negative. It's just a minute microscopic value. It doesn't really it's not so much in the quantity, it's just more designating whether or not that charge is positive or negative as to why it's important right now, okay? So, when you have an atom, you have the nucleus, which is made up of protons and neutrons, and the proton is positive, and then you have the electrons that are in orbit around the nucleus, and the electrons are negatively charged. All right, so this is a positive charge, this is a negative charge right here. All right, so these two opposing forces work to hold each other together, essentially. So it's this negative charge this is negatively charged in the same amount as this is positively charged. All right, so it's that electrostatic relationship between the two, along with centrifugal force, that keeps these electrons in orbit around the nucleus. All right, so electrostatic force can be either a repelling force or an attracting force, as we just talked about, right? Depending on if they're opposites or if they're like charges. All right. So once again, nucleus has protons and neutrons. The electron and the nucleus is positively charged, and then the electron is negatively charged. All right. So one thing that might help understand this also, and how this relates to other things. When you have an atom, you may have 2 or 3 rings of electrons, all right, that are spinning around the nucleus, all right. But what really concerns us is the outermost ring, which is called the valence ring. And any electrons that are on that outermost ring are called valence electrons. And the reason that's important to us is because, like I said earlier, one of the basic components of a electrical circuit is a conductor. All right, so we have conductors, you have insulators, and then you have semiconductors. So a conductor is what we use to get current from one place to another. So it conducts electricity really good. Like I said, it gets electricity from point A to point B. So it's what we use to do the work, to make things run. Okay, so insulators, in a nutshell, they oppose current flow, and they inhibit, like electricity can't flow through an insulator. All right, so typically, like, an insulator is what we use to cover a conductor, so that we can touch a conductor without being shocked, without becoming part of the circuit. All right, and then semiconductors they're a material that's not really an insulator and not really a conductor, but under the right conditions, they can be made to go either way. Okay, so we've talked about just a brief description of conductors, insulators, and semiconductors, right? So tying this back to valence electrons, what makes the difference between a good conductor, a good insulator, or a semiconductor is how many valence electrons that each one of them has. Okay, so if you have a conductor, then it's going to have is going to have 3 or less valence electrons. All right. So an insulator is going to have 5 or more valence electrons, and a semiconductor has 4 valence electrons. So the more valence electrons in this atom, then the more it becomes an insulator. So if you have a really good conductor, it's going to have one valence electron. But if you have an atom that has, say, 6 valence electrons, then it's going to become an insulator. And once again, so a semiconductor is one that has 4 valence electrons, right? And that basically means how well it conducts electricity. All right, is how many valence electrons it has. The less valence electrons it has, the better conductor it is. The more more valence electrons it has, the better insulator it is. Okay? So, examples of conductors that we typically use, we typically have either aluminum or copper conductors. They're really good conductors. If you have an insulator, a really good insulator, it might be porcelain or a plastic. Right? And then semiconductor, an example of a semiconductor would be like silicone that they make computer chips out of. Right? So, talked about that. Right? And now we're going to talk about magnetism a little bit. So I'm sure most people have probably messed around with a magnet and understand that, you know, there's a north and a south, right? So I'm just drawing a simple bar magnet here, all right? So you're going to have, whenever you have a magnet, you have a magnetic field that is around that magnet. And I mean, I understand that probably sounds pretty obvious, but like I said, I'm just trying to cover everything right from the basics. All right. Excuse me. So you have a magnetic field that exists around every magnet. All right. And that magnetic field is made up of what we're going to call magnetic lines of flux. That's what these little dash lines are that I just drew here. All right. So when these magnetic lines of flux, the stronger the magnet is, the stronger these lines of flux are going to be. All right, the stronger that magnetic field is going to be. And you know, a good way to think about that is, you know, what's the difference between, you know, the magnet you have maybe on your fridge holding up a piece of paper versus, you know, a magnet that you're using to hold a door open in a building somewheres. You know, one one has a stronger magnetic field than the other, right? Well, that's why, because one has a stronger magnetic field. It's a better magnet, all right? So these lines of flux, though, these operate just in the same way we were talking about how opposites attract, and then like particles oppose. So if you had another magnet here, and you had a north right here, these would try to attract one another. Whereas if you had a north here, they would oppose each other, right? So, talking about magnetic lines of flux, though, why these are so important is because whenever current flows through a conductor, it creates a magnetic field, all right? So if this circle that I'm drawing, let's say you're looking at a piece of wire and you're looking at it right head on. So this is right here, this is the conductor right here, right? So whenever there's a current flowing through a conductor, you're actually creating a north and south magnetic field that is created around that conductor. And the fact that that exists is the basis for how electricity really works, essentially. There's so many things that build off of this principle. Whenever current flows through a conductor, a magnetic field is created around it. The more current flows through a conductor, the stronger that magnetic field is. And there's things that you can do to make that magnetic field stronger. Like if you take a wrap of wire, or if you take a length of wire and wrap it around in a coil, that will make a magnetic field that has a given strength. If you take that same coil of wire and put it around an iron bar, that is going to take and put the same power to it. That's going to make that magnetic field even stronger. It's going to concentrate it and make it even more powerful. All right? So what I'm drawing here, And I'm no artist, so let's just get that out in the open right now. We've got to get used to that. So anytime you make what I've just drawn, where you apply power to a conductor to make a magnet, it's called an electromagnet. All right, and these magnetic lines of flux here, if these magnetic lines of flux cut across another conductor, then it will induce a voltage into that conductor. All right, and that's something for another day. But that's essentially, this is the basis of how electricity works, is with magnetism. All right. So, you know, how does electricity get from one place to the other, right? So typically you have a distribution point, excuse me, or a generation point, where, let's say you got, you have a hydro, all right, a hydroelectric power plant, and let's say it produces voltage. It produces 10,000 volts, all right. K is 1,000 volts, so 10 kV means 10,000 volts, all right. 10,000 volts, right? All right. But what you want to do is, because the higher the voltage, the less amperage, and we'll get into that later, you go to a transformer that will step the voltage up to, say, 115,000 volts, or 115 kV, all right? And then that goes out on the power lines that you see on the side of the road, on the side of the interstate, where you got like a big swath cut through the woods, and you see these big towers that are, 80, 100 feet tall, and they have big conductors running down through them. That's your transmission voltages, right? And then you go to a substation, where you take that 115 kV and you transform it back down. See, up here at this transformer, this was a step-up transformer for transmission. Now in a substation, let's say we're gonna step the voltage down from 115 kV down to 32,000 volts, 32 kV. All right, and then that is your distribution voltage. So transmission, transmission is like when you got to send voltage, from one county to the next. All right. And then distribution is when you got to go from the substation to, spread power throughout the town that the substation's in, or the next town over. It doesn't have to go nearly as far. So substation, distribution, so 32 kV, 32,000 volts distribution, and then it may even dump down further to, say, 7,200, 7.2 kV at another smaller substation, right? So 32 kV down there, and then that's when it goes out to the houses. All right. So typical voltage on a residential service is 120 volts and 240 volts. So everyone's house that's getting powered in this country, well, I shouldn't say everyone, but 95% of them are going to have 240, 120 volts. So that transformer that's out on the pole that feeds your house has 7.2 kV coming in and 240, 120 volt going out. All right. And then that's where it actually goes to your house. All right. So this is just basic, this is just the basic distribution system between the generating facility through the transmission lines, down to a substation, out to distribution, from distribution voltages to maybe smaller substations, and then to the transformer that's actually hanging on your pole and getting power to your house. And it would be essentially the same thing, you know, even going for a business. Let's say you have a 7.2 kV down to 120, 208 volts for a business, you know. So, you know, this could power either a house or a business. So that's just some of the basics of electricity. There's going to be more coming as far as how, you know, getting into Ohm's law, the different values, calculating the different values for voltage, current, resistance, and also getting into watts, and how that applies in an AC circuit or a DC circuit. Definitely be talking about magnetism more. Once again, this is just a basic overview of it. Yeah, hope it helped you.